Stanford University.
So the questions that were asked to me tonight are more or less by accident, are exactly the ones that I want to address tonight. Weak gravitational fields, linearity versus nonlinearity, and gravitational waves. Again, working out the equations of general relativity is always unpleasant. And we're not going to do it on the blackboard. They would fill the blackboard, even for simple things, and they probably would not be terribly illuminating. To learn this subject, really how to compute and how to solve its equations and so forth, I think you just have to sit down and do it. On the other hand, the principles are straightforward enough, and it's easy enough to say what you get when you do solve the equations. So that's the way we'll talk about gravity waves, by writing down the equations and then writing down the solutions. Now, we're interested in what could be called weak gravitational waves. Weak gravitational waves means that the amplitudes of the gravitational waves are small enough that you can make approximations such as the amplitude squared of the gravitational field is 0. When a quantity is small and you're expanding an equation about the smallness of that quantity, the usual rule is to ignore things which are higher order in that small quantity. All right, so we start with an equilibrium. We're talking now about fluctuations or perturbations about an equilibrium situation. And the simplest equilibrium solution of let's write Einstein's equations first. Einstein's equations, let's take the case without any matter, no energy momentum tensor. Then the equations of motion are just r mu nu minus 1/2 g mu nu. R is equal to 0. That's called the Einstein tensor, g mu nu equals 0. And it can be simplified. If you take the trace of both sides, the r here is the trace of the Ricci tensor. If you take the trace of both sides, you will discover that r, the scalar curvature r, is equal to 0. And once you know that, you can ignore the second term in the equation. The equation is simpler. That doesn't really matter because we're not going to write down the details anyway. But this is the equation of Einstein in a context in which there is no energy momentum tensor on the right-hand side. All right, what's an equilibrium situation? An equilibrium situation, first of all, means a solution which has no time dependence. There's really, and which also doesn't have any matter on the right-hand side. Matter is another word for the energy momentum tensor on the right-hand side. No right-hand side. There's really only one equilibrium situation. The equilibrium situation is just empty space. Empty space is time independent. The by empty space, I mean empty flat space. No curvature, no interesting gravitational field. And in that case, the metric, g mu nu. Now, I'm not going to say the metric is equal to such and such. The metric depends on the coordinates you use. If I wrote that the metric of a flat plane is just the Kronecker delta symbol, you would correct me and say, no, the metric of a flat plane is not the Kronecker delta. A possible metric expressing the flatness of space would be the Kronecker delta. But if I used other coordinates, the metric would not be the Kronecker delta. Use curved coordinates, use polar coordinates, use any other kind of coordinates. What's special about flat space is that you can find coordinates in which the metric has a nice simple form. The same is true in general relativity. Flat space-time with no gravitational field, there is a choice of coordinates in which the metric has the simple form of eta mu nu. And let me just remind you what eta mu nu is. Eta mu nu is a matrix. Let's just write the matrix. I think with the notations we've been using in this class, I think it's 1, minus 1, minus 1, minus 1, 0, 0. No, sorry, that's incorrect. It's 1, 0, 0, 0, 0, 1, minus 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Which row and column corresponds to time? The first one. T, X, Y, Z, T, X, Y, Z. This is, and so forth. Okay, so that's the metric of flat space-time, 1, minus 1, and 3 pluses. And it's an equilibrium solution. It is a solution of the Einstein field equations. The Einstein field equations say certain components of curvature are equal to 0. This is a geometry, or this is a metric that has no curvature at all. And so it is a solution. If you plugged it in, you would find it's a solution. In fact, it would be trivial. One step. Now, let's think about something which is close to empty space. Far away, some complicated thing is happening, far away, too far away to be interesting to us, or at least to be close enough for us to directly observe. There's something going on. A binary pulsar is rotating around and doing some complicated emission of gravitational waves. Close by, the gravitational field may be very strong. Even the gravitational waves might be rather strong. But if you go far enough away, the gravitational radiation, the gravitational waves that are produced by this thing are going to be very weak. Right? What does weak mean? Weak means that the true metric can be chosen, again, I emphasize, can be chosen to equal eta mu nu plus something small. Small means that its components are much smaller than the ones which appear here. And that small thing is usually called h mu nu. As far as I know, it's called h because h is the letter after g. I don't know any other reason for h. H mu nu, unlike eta mu nu, is in general a function of position. It's also, when I say position, I mean position and time. It's a function of the coordinates. It varies from place to place. And it might describe a wave. We'll come back to waves in a moment, but let's, what are we going to do with this? We're going to take this metric, calculate from it r mu nu, and set it equal to 0, and that's going to give us an equation for h. Now, the equation that you actually get from h for h, it's not big enough to fill the whole blackboard, but it's big enough to be quite unpleasant. And so I'm going to be schematic. I'm going to show you what goes into it. First of all, what is r? R is a combination of components of the curvature tensor. I'm not going to write the curvature tensor. I'm just going to remind you what it contains. The curvature tensor itself, the thing with 4 indices, contains one term which is a derivative with respect to position, with respect to x, and I'm not even going to write which x. It contains lots of different derivatives depending on the index structure. Derivative of the Christoffel symbol. So it contains a first derivative of the Christoffel symbol, and secondly, it contains the Christoffel symbol quadratically, squared, or Christoffel symbol times another Christoffel symbol. This is really all, this is as much detail as we're going to do. I could put the indices in here and remind you where the indices go, and there are various terms which look like this, there are various terms which look like that, but this is good enough for us. What about gamma? What about the Christoffel symbol? If you remember, well, first of all, it contains a factor of 1/2. It contains the metric tensor with components upstairs. The metric tensor with components upstairs is simply the inverse matrix of the metric tensor itself. It can also be expanded in powers of h. The first contribution to it is just the eta symbol itself. So the inverse, eta is its own inverse matrix. And so it begins with a g to the minus 1. I'll be more specific in a minute. And then it has derivatives of g. It has various kinds of derivatives of g. Now come back to here. G inverse, that contains, again, things like eta, probably minus h. But whatever it is, it contains the eta symbol plus a small correction. The metric tensor with upper indices, if you only had eta, would basically be the same eta. And then h would appear as a correction. All right, so G inverse here, this would contain things like, this is a wiggly equal sign, which means not equal at all. It would contain things like eta minus a small correction or plus a small correction. That's not important for us. But then the derivative of g, that only contains h. Why? Because the derivative of this metric tensor is just 0. All it contains is zeros and ones. The derivative of zeros and ones is 0. And so in the approximation that we're working in, the derivative of g just contains derivatives of h. Let's just call it derivative of h. Okay, let's look at what we have here. This is the Christoffel symbol. It contains one term which has 1 power of h. Incidentally, h is small, and we'll also assume that its derivative is also small. If you have a small number, a small function, and you differentiate it, it's equally small in general, unless it has very sharp points or something, which we'll assume it doesn't. So the derivative of h is also considered to be a small thing. Eta times h is once small. H times the derivative of h is twice small. It's quadratic in the fluctuation or in the small gravitational field, so we ignore it. Too small to be important. If h is 0.01 and derivative of h is 0.001, then h times h is 0.0001? Whatever, very small. All right, so we can ignore this. And eta times h we'll just call derivative of h. Just call it derivative of h. So the Christoffel symbol itself is just in the approximation of weak gravitational radiation. The Christoffel symbol itself is just proportional to some derivative or some collection of derivatives of h. What about the Ricci tensor then? The Ricci tensor will contain derivative of gamma, and that's going to be second derivative of h. It's going to contain various kinds of second derivatives of the gravitational field. Incidentally, h is called the gravitational field, or the field of a gravitational wave. And then over here, it's going to contain plus derivative of h times derivative of h. Gamma times gamma is quadratic in derivatives of h. So immediately we say this is much smaller than this, and we ignore it. So whatever the devil this Ricci tensor is, it's composed out of simple second derivatives of the metric tensor. From that we can conclude that Einstein's equations have a relatively simple form. There's still plenty of indices around, and the number of different terms involving second derivatives of h are significant, It's not a, it's complicated enough I don't want to write it down on the blackboard, but it is basically built out of second derivatives with respect to position and second derivatives with respect to time, and maybe even some terms which have a derivative with respect to position and a derivative with respect to time. And furthermore, there are several components of it. There's not just how many components of it. Well, the Ricci tensor has a mu and a nu, so it has two components. What comes out has two components, but the whole works, whatever it is composed of second derivatives of h. Okay, so our equation of motion is some kind of equation that looks like this. Equations of that form, especially in relativity, are usually wave equations. But just to remind you what a wave equation for an ordinary wave looks like. Let's say a wave moving down the z-axis. A wave moving down the z-axis also satisfies an equation that looks like this. Let's say the wave field, let's call it phi. The wave field phi will satisfy an equation like d second phi by dt squared is equal to d second phi by dz squared. This is the simplest wave equation that you can imagine, and the solution to it are waves which move either to the right or to the left. You can add waves which go to the right and the left. It's still a solution. So you can take a wave which looks like this, add it to a wave moving to the left. The sum is still a solution because the equation is linear. Okay, so this is, or we can, let's write it this way. This minus this is equal to 0. If we had more directions of space, the structure of the equation would be a little more complicated. Instead of just derivative of phi with respect to z, we would also have a sum of terms plus second derivative of phi with respect to x squared plus second derivative of phi with respect to y squared equals 0. But it's evident that there's a family similarity between the kind of equation which occurs here and the kind of equation which occurs here. In fact, by clever manipulation, you can make these equations. This is not just one equation, incidentally. There's an equation for each mu and nu. Let's put a bracket around here and just remind ourselves that there are 4 times 4, 16 components of r mu nu. Now, they're not all independent, and it is really quite a bit simpler than that. But still, in principle, there are 16 components, 16 equations. In that respect, it's somewhat similar to Maxwell's equations. Maxwell's equations have the form of wave equations, for example, for the electric and magnetic field, but there are several components. There are 3 components of electric field, 3 components of magnetic field. Sounds like there's only 6 equations, but in fact there are 8 equations, Maxwell's equations. And this is the same sort of thing. Several equations, but all of similar form. Any questions?
One question, doesn't that derivative put 2 indices, doesn't it actually have 4 indices?
Doesn't it have what?
4 indices. 2 go with the derivative and 2 go with h.
Yeah, but they were contracted in many ways. Remember, yeah, that's correct. But remember where r mu nu came from. It came from a thing with r mu nu sigma tau, or upstairs or downstairs indices. And then we contracted them, put a nu upstairs here, so that nu disappeared as an index, and we just got the Ricci tensor. So yes, with 2 derivatives and 2 components to h, we certainly can make how many? Whatever number. We can make a number of different combinations, much more than just 2 indices, but the combination that we're interested in is contracted in such a way that there's only 2 indices and only 2 equations left over.
Excuse me.
Yeah.
On that contraction, when you have the index upstairs, doesn't part of the contraction involve introducing the metric again, or not?
Yes, it does. Good. Right. So part of contracting involves introducing the metric again. But again, the same thing is true. The metric is eta plus h. R is composed out of derivatives, so it already is small. It already is small, and if you multiply it by another small number, it's doubly small. I think that's what you're asking.
Well, yeah, but
Yeah.
then won't you get terms of the form h times second derivative of h?
Yes, but they're counted as infinitely small.
Okay, so they're
Right.
smaller than the
Yes, anything that involves an h multiplied by another h, or a derivative of h times another derivative of h, or an h times a derivative of h, is dropped in this approximation. Now, this is an approximation, but it's a well-defined approximation in that it is well, technically it's the linearization of Einstein's equations, which simply means you throw away everything of higher power. Yeah. But it is a good approximation when the gravitational radiation or the gravitational wave is weak. Okay, so we have equations of this form, which we're not going to specifically write down. They're kind of messy. But before we discuss them, or before we discuss the solutions, you might ask yourself, well, I originally told you that that it's not that the metric of flat space is equal to eta mu nu, it's that it can be chosen to be equal to eta mu nu. That means that there are other ways to represent flat space. Make a coordinate transformation. Make a coordinate transformation on eta mu nu, and the metric changes, but it's still exactly the same solution. And so what that means is that there must be solutions of these equations which look like they're non-trivial, but really are just that all they really represent is flat space, but in coordinates where the coordinates have little ripples in them. In other words, supposing I take the flat blackboard, I maintain that the flat blackboard is a solution of Einstein's equations. Well, not really. Well, it is, yes, but not in the sense I mean here. It is a flat space. Okay. It can be represented by a metric delta mn, let's say. M and n stand for x and y. On the other hand, there's nothing to prevent me from introducing coordinates with little wiggles in them. Well, we could start with coordinates. Let's say we start with coordinates, which are the good Cartesian coordinates. Let's call them x, standing for x and y. Well, yeah, let's call them x, x and y. All right, x and y. And then we can introduce new coordinates, x prime and y prime, where x prime is just x plus a small change. We could call that plus f sub x of x and y. It's a coordinate change. A coordinate change is x prime is some function of x and y prime is some other function of x and y. That's a coordinate change. Here, the coordinate change is taken to be almost no coordinate change at all, plus a small little correction. Same thing for y. Y prime is equal to y plus, let's call it f sub y of x and y. I have not changed the space in any way. All I've done is change coordinates and perhaps put some little wiggles. If f has some wiggles in it, then the new coordinate axes might have, the new coordinate lines might have some little wiggles in them. And now the metric, if I rewrite the metric for the prime component, so let's say, let's take the case, let's assume the metric in the primed coordinates is just dx prime squared plus dy prime squared. I'm working backward. I'm supposing that the primed coordinates are the nice coordinates, the nice Cartesian coordinates, and the x and y coordinates are the slightly curved ones. All right, what is the metric? The metric, this is just a blackboard now. We're not doing space-time, just a blackboard. The metric of the blackboard is dx prime squared plus dy prime squared. Let's work it out for fun in x and y. Okay, so what is dx prime? We work out what dx prime is. Dx prime, comma, dx prime is equal to dx plus the derivative of f sub x with respect to, let's call it x sub xm. M could be either x or y times dxm. And likewise for y. We figure out what dy prime is. That's dy plus a small correction. And you plug it into here. And what do you find out? You find out that the x prime squared plus dy prime squared is not dx squared plus dy squared. It contains dx squared plus dy squared, but also contains other cross terms, dx times this and dy times that. And if you work it out, what you find out is that this is equal to dx squared plus dy squared Now I am assuming that f is small. And we're going to assume that f is small, and that means when I square dx prime squared, I can drop dx squared. Likewise for y. So what I'm going to get is a correction. And the correction can be called h mn dxm dxn. In other words, just by squaring out the x prime squared and dy prime squared, substituting in, you'll discover that there's a small correction to the metric tensor. Now, does a small correction to the metric tensor mean that the geometry of the blackboard has changed? No. It just means that the coordinates that I've used have wiggles in them. You can work out, it's nice to work out, it's a little exercise. Work out what the correction in the metric is, dropping anything which is quadratic in f, dropping anything which is higher order, and I'll tell you what you get. You get that HMN, m and n now just run over x and y, is equal to dfm by dxn plus dfn by dxm. That will mean nothing to you until you try to work out an example, or until you try to prove it. This is the correction to the metric. It's a correction to the metric, which is small. Why? Because I chose f to be small. It has the form of a small perturbation on the metric, but it doesn't represent anything. It represents just a trivial change. So there are some, let's call them perturbations. Perturbations mean a small change. Perturbations on the original form of the metric, which are trivial. They don't represent anything. Likewise here, there are small fluctuations that you can write down which just represent curvilinear coordinates in space-time. How do you get rid of that? How do you get rid of it and eliminate the phony solutions which automatically solve the equation because they're just flat space, but which don't represent any real physics? And you do it by imposing more equations more equations on the metric that sort of cut away and divide out and eliminate the unwanted spurious solutions. I could write down the equations. It's not important. They're just equations which tell you get rid of the spurious coordinate ambiguities. And you can do that in a wide variety of ways, a wide variety of conditions that will allow you to eliminate the unphysical, meaningless solutions of Einstein's equations. Once you've done that, and you've imposed all of the Einstein equations here, once you've done that, incidentally, the equations become pretty simple, and in fact, all they become is wave equations. They become wave equations. They become several different equations. They become, first of all, just perfectly ordinary wave equations for the components of H. Same kind of wave equations that I wrote down. Where did I write them down? I guess I erased them. D second phi by dt squared minus d second phi by dx squared, blah, 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 y squared and z squared is equal to 0. All right, so there's some, and let me write them now in the correct form. Instead of phi, we have h here, h mu nu. Each component of the metric tensor, or each component of the fluctuation, satisfies a wave equation. That means that all the components of the wave equation, all the components of the metric just move down the axis like waves. And there are waves. On the other hand, there are also some constraints. The constraints come, there's a lot more equations. How many equations are there? Well, there are more equations than one for each mu and nu. The reason that there are more equations is because you have to divide out this spurious fake solutions that are there because of the coordinate ambiguity. Once you do that, you find out that the physical solutions, the ones that really have meaning, I'm going to classify them now for you. Supposing we have a wave moving down the z-axis. Let's suppose we have a wave moving down the z-axis. What does a wave moving down the z-axis look like? Wave moving down the z-axis, if it were just a simple wave, would just be phi is equal to something like some number times sine of k times x minus z. Times z minus t, times t minus z. Z minus t? T minus z, doesn't matter. Same thing. This is a wave that at a fixed instant of time is just a sine wave, and it moves down the axis with unit velocity. Unit velocity here means the speed of light. All right. Now, each one of the components will have a solution like that. Each component will be proportional to sine k times, what is k, incidentally? It's the wave number. Right. So it's the frequency of the wave. It's the frequency of the wave. It's also the wave number, the number of oscillations per unit length. And of course, it can be anything. It can be any number. Short wavelengths have large k. Long wavelengths have small k. OK, so that's a typical solution of a wave equation. And the solutions to this equation here are all of the same type. H naught is equal to some function. Well, there's a coefficient here. Let's call the coefficient phi naught. Phi naught is just a number. All right, each component is a function of t and z, which is proportional to the same thing, sine k times t minus z, times a number, which we can call h naught. Let's put mu and nu here. Mu and nu. And this is not a function of position. It's just a numerical coefficient that multiplies the sine of t minus z. And that's about all you can write down. This is the nature of a gravitational wave. Each component of the metric behaving like a wave moving down the axis. However, as I said, there are more equations. The additional equations, there's a good number of equations here. And when you impose them all, you find out, before we do this, let's just remind ourselves something about electromagnetism. In electromagnetism, we do the same thing. We solve Maxwell's field equations. We can solve Maxwell's field equations either for the vector potential or the electric and magnetic fields. Right. But when we write down all the equations, we find some constraints. The constraints are called transversality of the field. Does everybody know what transversality of an electromagnetic field means? It means that the electromagnetic field, the electric and magnetic fields, always point in the directions perpendicular to the motion of the wave. Not only are the solutions waves, but they're transverse waves, meaning to say that the electric field and the magnetic field points one way, the electric field points the other way, and the whole thing goes down the axis, oscillating as it goes down the axis. Very similar things happen here. The waves have to be transverse. To say that the waves are transverse means that the time components and the z components of h are zero. The only components of h which are allowed to be non-zero are the components in the plane perpendicular to the direction of the wave. So if you substitute this in to all the equations, the full set of equations here, including the ones which remove the fake spurious fluctuations, you find that a gravitational wave has a very, very simple form. Well, it does have this form. A set of numbers, h nu, but the only components that are allowed, let's say this is z, x and y, I'll call I and j. I and j represent the directions in the plane perpendicular to the motion of the wave. Then the only components which are allowed are h, I, j times sine kx, kz, kz minus k times z minus t. So if you're looking down the z-axis, you see in front of you the xy plane. You see in front of you the xy plane. There's the xy plane. And the xy plane at each z and t, in other words, a slice, here's on my slice, I slice it at a given location at a given time. At a given location and a given time, the metric of the two-dimensional plane, I slice the wave into two-dimensional planes as I go down the axis here at a fixed instant of time. And what I have here is a metric for each z, which looks like, where is it? Right over here. With only only components, with the components only in the plane perpendicular to the motion of the wave. And the components are simply numbers. At each z and t, the metric is simply a set of numbers. There's one more equation that it comes from Einstein's field equations, and it says that the trace of hij is equal to 0. In other words, hxx plus hyy is equal to 0. That's it. That's the whole set of equations, and what it tells you is that the metric of a gravitational wave is h naught naught equals 0, h z naught is equal to 0, hzz is equal to 0. In fact, h anything with either a time component or a space or a z component are equal to 0. The only components which are not 0 are hxx, hyy, and hxy, hyx. The metric tensor is symmetric. The metric tensor is symmetric, and so hxy and hyx are the same. And finally, hxx plus hyy is equal to 0, which means that hyy is minus hxx. Well, hyy is equal to minus hxx. That's pretty simple. But what does it mean? First of all of these vary with z and t. They vary only with z and t. If the wave is going down the z-axis, then by definition, the variation is along the z-axis. And so hxx is some number to begin with, times sine kx times sine kz minus t. This one is h naught yy sine k times z minus t. And likewise, this one is h naught xy sine kx. Yeah, okay. Okay, so think of a series of layers. Let's look at it at a fixed instant of time. At a fixed instant of time, for example, time t equals 0. As we move down the z-axis, there's a perturbation on the metric. The metric tensor is a little bit different from just a flat space metric. It oscillates as you go down the z-axis. And the components that oscillate are the components that have to do with the metric of the plane perpendicular to the wave. What does it mean to have an hxx? Well, let's just take the case of hxx. If there's an hxx, that means that the xx component of the metric is a little bit different than 1. The xx component of the metric was originally 1. That's eta xx. It's 1 plus this little bit. Blah, blah, blah. Plus this little bit. That means that proper distances along the x-axis are a little bit different. That actual distances, let's say between x equals 0 and 1, or let's say between x equals minus 1 and 1, that the actual distance, remember, the metric tensor is the thing which tells you the actual distance between points. The coordinates are just labels. The actual distance between point minus 1 and point plus 1 is a little bit different than it would be if this perturbation weren't here. Either a little bit larger separation or a little bit smaller separation, depending on the sign of hxx. For example, if hxx is positive, then the actual physical distance between here and here would be a little bit larger than 1 meter, supposing we're working in meters. That would mean that a meter stick doesn't quite extend from minus 1 to 1. What about gyy? Well, we'll take hxx to be positive. If hxx is positive, did I say that? Yeah, I did get that right. The distance between minus 1 and 1 is a little bit bigger than a meter, and therefore a real meter stick would be a little bit shorter than the interval between minus 1 and 1. Not because the meter stick is necessarily shorter, but because the coordinates are such that on that surface there, the distance between -1 and +1 would be a little bit bigger than a meter. All right, what about GYY? GYY is equal to 1 minus HXX. Minus HXX because Einstein's equations tell us that some of these two are equal to 0. That in turn tells us that a meter stick oriented along the y-axis, let's say from y equals 1 to -1, here's again 1 minus 1, a meter stick would look a little longer. The distance between +1 and -1 would be a little bit less than if you only had the 1 here. And so a meter stick over here would look a little bit longer. Now, this would be nothing but a squeezing of the coordinates so that you would be choosing coordinates along the x-axis where the meter stick was a little bit less than 1 unit and the meter stick along the y-axis was a little bit greater than 1. It would be nothing at all. It would be nothing significant except for the fact that it changes as you go down the axis. As you go down the axis from one point to another, or if the wave were passing you, imagine better even yet, the wave was passing you. The wave is passing these meter sticks. All right. After a brief amount of time, the h's will change sign. Not this sign, but SIGN. The sine wave oscillates. So after a brief interval of time, one half cycle of the wave, HXX has changed sign, HYY has changed sign, and the result is after a brief interval of time, the meter stick will look a little bit short in these coordinates along the y-axis, and the meter stick will look a little bit long along the x-axis. Yeah?
The meter stick is held together electromagnetically. It's
Yeah.
not changing length. So you're talking
No,
about
these are coordinates.
Right, you're talking
That's
about
right.
two little test masses. They would move back and forth.
In fact, two little test masses would move back and forth, but not because, the meter stick is 1 meter long. Okay, it's always 1 meter long, but an oscillating wave is going back and forth, perturbing it. A real wave of curvature. This is real curvature. And if you like, I think one way to imagine it, well, the time dependence of this wave really does exert tidal forces. They're tidal forces. The wave has curvature. The wave is moving past here. It's a kind of tidal force. And the nature of the tidal force is to actually cause the meter stick to be compressed, stretched. And the way that it's compressed and stretched is that when it's compressed horizontally, it's stretched vertically. When it's compressed vertically, it's stretched horizontally. So if you like, this wave going by a meter stick, or for that matter, if it were just two test masses, if it really were just two test masses, the two test masses would oscillate back and forth. If instead of taking a meter stick, you took a square piece of plywood, the square piece of plywood would be deformed this way and then reverse. This way and then reverse. Now, it's interesting, there is another solution. There's another solution in which not hx and hy are non-zero, but in which hxy is non-zero. That would be a metric which would look like the Kronecker delta mn, or delta ij, plus a little matrix which had an hxy over here and an hxy over here. That still has hxx plus hyy equal to 0. There is no hxx hyy. If you think about it a little bit and just spend a little bit of time figuring out what this means, it's also exactly the same kind of thing, except that the squeezing and stretching are along the 45-degree axes. Stretch this way, squeeze this way, oscillating. It's not a new thing. It's not a new solution, except that it's the original solution turned by an angle. In fact, any solution that you write down, which is a superposition of these two kinds of solutions, any solution is a linear superposition of the two solutions, and they correspond to some orientation of axes, where along those axes, the compression and expansion are along those tilted axes. That's all there is. That's all the kind of gravitational waves there are. You pick a set of axes perpendicular. First of all, you pick the direction that the gravitational wave is moving. Yeah?
What can you use to measure this compression that does not change?
A strain gauge. A strain gauge. This will create honest, real stresses in the piece of plywood. A strain gauge will register them. When this wave is going past, if the wave was static and not moving, then this piece of plywood would really be unaffected. Everything would be simultaneously squeezed or stretched the same way. The rulers which measure the plywood, the strain gauges which measure, but it's the oscillating character of the solution which really does create real honest stresses and strains in it. It does have real curvature, and this is what it does.
What triggers the gravitational wave? Like an electromagnetic wave is triggered, so, by a current, say.
Or by a moving charge, or a charge. For example, one charge of an electron going around a proton will create electromagnetic waves. And the same thing, a star or a black hole or a pulsar or whatever it is in orbit around another one, a binary pulsar, for example, the famous binary pulsar, two very, very concentrated masses which happen to be rotating around each other at a rather small distance. Neither one is a black hole. The whole thing is not a black hole, but it is a very, very strong gravitational field. They're going around each other, and in going around each other, the accelerating masses create the gravitational waves. So now, near the binary pulsar, this is a bad approximation. The gravitational field is too strong to linearize the equation this way. But if you get back, a few radii, a few distances away, then the wave spreads out, dilutes itself, and gets weak enough that this becomes a good approximation. So, okay, so if you had the binary pulsar is over there, and you're standing back, the wave is coming at you, let's say the axis between you and the binary pulsar is the z-axis, then what you'll see coming past you will look like this. And what it will do is it'll cause stresses and strains along perpendicular to the line of sight to the pulsar. Yeah. Yeah.
To clarify, that red meter stick you have is right behind you.
Yeah.
The red meter stick is an abstract meter stick, not a real physical meter stick.
Oh, it could be a real physical meter stick.
But it changes, right?
It has stresses in it.
Other than the stresses and strains, how do you measure it with a variable meter stick?
Well, I think the way you measure it is by the stresses and strains that are induced in it. Yeah. It's hard to say that it's not a meter because it's by definition a meter stick. But
it's a variable. In essence, it's variable.
Yeah. Yeah, if you had a steel meter stick and a wood meter stick, they would probably react differently. So once these stresses are applied, once the stress due to the curvature tensor here, and it's a real thing, the curvature tensor It is a kind of tidal force. Once these tidal forces are applied, the meter sticks, the 2 meter sticks, the steel one and the wood one, will stress by different amounts in general. So if you measured the wooden meter stick with the steel meter stick, I'm not sure which one would be bigger and which one would be smaller, but they wouldn't match up precisely, yeah.
Would this be how you would build a gravity wave
Just
detector?
here,
Sorry.
yeah.
That's kind of the point I was making before.
Yeah.
A steel meter stick has got a big elastic modulus. It's
Yeah.
not going to shrink very much when the wave goes past. But if you have 2 test masses that are floating right at the ends of the meter stick, they have no elastic modulus. They'll move right with the space-time.
That's right. Well, no.
See them move relative.
No, they won't move quite with the space-time.
They'll be accelerated.
They'll be accelerated.
Right.
Yeah. So they'll start ringing. Now, if you want to detect a gravitational wave, what you want to do is create some system which has a resonance at the frequency of the gravitational wave. You know what a resonance is? A resonance means that the system has its own natural frequency of oscillation, which is the same as the oscillation frequency of the wave. Then you would have a driven system being driven at its own natural frequency, and under those circumstances, the response will be particularly big. So if you wanted to detect a gravitational wave, let me say that the gravitational waves that we expect in astronomy from different sources, believe me, I'm not an expert at this, but I know enough about it to know that the h mu nu, which are produced by a distant gravitational source, are very, very small. They're so small that the dimensionless strain on a steel rod or something like that would be something like 10 to the minus 21. Really, really small effects. The fact that people even contemplate measuring them is quite astonishing, but it seems they can be measured. And
Hasn't been detected.
no.
But there is a system that measures the legal system. There is a system that built in 2 places, I think one in Louisiana and some other place, which is measuring that by interference of laser wave, I believe.
I'm not sure what you're asking.
LIGO or
LIGO.
Yeah.
LIGO.
Yeah.
But they haven't.
LIGO is a gravitational detector.
It's not sensitive enough.
It's not a steel rod, it's a pair of mirrors which are monitored by laser beams, interference effects due to the relative motion and so forth. But basically, a gravitational detector is a system which is allowed to be set into oscillation either this way or that way, and yeah.
Is there a velocity that comes out of those solutions?
Oh
by
yeah,
itself,
the
or
speed of light.
Oh, okay, it's not
Yeah.
put in artificially in advance by
No,
Einstein's
it's the
equation?
speed of light.
Okay.
So if you saw a gravitational collapse or the collision of 2 black holes would make, and that happens from time to time. When I say it happens, I mean to say that you can estimate roughly from observed facts how many black holes are out there, and you can guess how many black hole collisions take place every year. And if I remember, I think within range of the best imagined detectors, if I remember, I think it's about 1 black hole collision per year. So it's a lot. So in principle, if it was possible to detect a black hole collision through other means other than gravitational radiation, you ought to see the signal at the same time as the gravitational radiation. Gravitational radiation is a pretty weak effect when you're far back, but from the collision of 2 black holes, it's an enormous effect when it's much bigger than any other kind of radiation that's emitted. So if the collision is taking place at large cosmological distances, it can be the case that the only way to detect it would be through gravitational radiation, gravitational waves like this. That's why it's interesting, because it's a new window for astronomy. Okay, that's what gravitational radiation is, or that's what gravitational waves are. They're real. I mean, you asked me if gravitational radiation has ever been detected. Yes and no. It's never been detected by direct detectors, but just like electromagnetic radiation, for example, from an orbiting system, radiation carries off energy. Carrying off energy means that as two systems are rotating about each other, they will lose energy, and in losing energy, they may speed up a little bit. They will speed up a little bit due to the loss of energy. And so the study of this binary pulsar that's out there, which has all the properties necessary for gravitational radiation to be emitted from it, when the timing of the the rotation of the two systems about each other, the frequency is changing a little bit in time, exactly as would be expected, quantitatively exactly as would be expected from the system if it were emitting gravitational radiation. Gravitational radiation is the main thing which would cause its energy to change, and it works out exactly right. So,
What sorts of frequencies are we talking about?
milliseconds? I think milliseconds. Yeah, I think. But you look it up, I'm not sure. It might be a little slower than milliseconds. Milliseconds is what a pulsar does when it rotates around its own axis. It might be a little slower than that.
I think, if I remember correctly, it's days.
Oh, days. Okay, days. Yeah. This is two stars going around each other. What am I saying? Milliseconds? No. Milliseconds is for the rotation of the pulsar. These are two stars going around each other. It's not take back what I said. Okay, yeah.
We arbitrarily took x and y as two coordinates that we decided to put them on a flat line. What about if we took x and t? In other words, how would it affect space-time rather than just the space?
This is the time direction. The wave has a directionality along which it's moving. The wave is transverse, which means the only components that have physical significance are the ones in the plane perpendicular to the direction of motion of the wave. The other components are either not there, or they correspond to a wiggle in the coordinates. The other components are either wiggles in the coordinates, or they're not there. Yeah.
I looked it up. For the original binary pulsar, where the detection was made, it's 7.75 hours.
Okay. Geometric mean of a day and right. How much has it changed over the period that it's been observed, though? A very small number.
About 30 seconds.
Really? That much?
Yeah, but it's been looked at for decades.
Yeah.
So time is actually oscillating as well. Is that what you just said?
It's not, time is not oscillating. The wave is oscillating with time. If you stood in one place, the wave would oscillate with time. Yes, but you were going to ask.
Well, but time is one of these coordinates, right? In fourth-dimensional space.
Time is a coordinate.
And it is orthogonal to z.
No. When I said orthogonal to z, I meant the space direction's orthogonal to z.
But there is time, right?
There is time. And the components of the metric, which have a time component in them, all are equal to 0. It's very much like an electromagnetic wave. The electromagnetic wave also has space and time, or electromagnetic field also has space and time components. The vector potential has space and time components. In a wave moving down the z-axis, only the transverse space components of the vector potential are there. So it's very much like that.
You said before that H00 and H0x, H0y, H0z are all 0.
Yep.
So there's no curvature in the time direction.
Well, no, there is curvature in the time direction. Remember something, yeah, the h's in those directions are non-zero, but when you differentiate, you can differentiate with respect to time and get the time into it, right. So derivative of h, let's say xy with respect to t is not equal to 0. And remember, the curvature tensor has 2 derivatives on h, so you can get a whole collection of different kind of components. Yeah. Yeah. But still, it's a very special kind of curvature that, that's not generic. Okay, that's gravitational waves. You can learn more about them by any good book on general relativity, which will write down the details of these equations. You know, they will fill about 1 blackboard. And they won't be terribly illuminating, but the basic principle I've told you. Any other questions? Yeah.
So
Art.
we start out with Einstein's equations, which are nonlinear. We wind up with a wave equation, which I believe is linear.
Only because we made the approximation of a very small h.
Okay, so it's got nothing to do with getting rid of the non-physical solutions?
No, no, no. The linearity is because the wave is weak. Generally speaking, I tried to explain before, small oscillations about an equilibrium, and the approximation that the oscillation is very small, are linear. So this is linear because of an approximation that h is so small that the square of it is 0. Any other question? Yes?
If you do this approximation like we did, and then you go back at the end and see how far off it was from an accurate solution, you know, how much error is there?
Depends how big h is. If h is 0.001, the corrections will be 0.00. If h is 1/10, the corrections will be 1%. Whatever h is, the corrections will be of order the square of it. Yeah. So right. So that's something. Yes, that's something you always do when you make a linearized approximation. You always check at the end that the corrections to it would be small. But they will be if h is small enough. Yes?
If you make h much larger so there is a component of a higher order, would that affect the fact that I and j are perpendicular to the z-axis? Would that?
No. No. But what it will affect is whether waves will pass through each other. They won't. They will scatter off each other. Right. No, the wave will maintain, that's a good question, but the wave will maintain its transverse character. Yeah.
In a mechanical wave, the magnitude of the mechanical wave is related to the energy and the stiffness of the material.
The energy and the stiffness of the material, yeah.
Is there any sense in talking about the stiffness?
Yeah, yeah. The stiffness of a material determines the velocity of propagation through the material. So you can substitute for stiffness, you can substitute velocity of propagation. Electromagnetic and gravitational waves are extremely stiff. They are the stiffest things possible, in that the speed of light, and that they are both governed by the speed of light. So in the old days when people thought about the ether and things, and the mechanical properties of the ether, they attributed a stiffness, what is it called, a Young's modulus or whatever it's called, to the ether, and it was a very, very big very, very big coefficient of whatever it's called, because the speed of light is so much larger than the speed of propagation, for example, through a metal beam. So we no longer really think of it as a stiffness, but if you did think about it as a stiffness, you would say that the space on which these waves move is very stiff.
Well, it's really the stiffness divided by the density, isn't it?
Mm-hmm.
So either it's very stiff or there's not much density.
Yeah, and only the combination of them appears in the propagation of light. Right, that's true. It's just one combination, namely the velocity, which appears. Right. True enough. Okay. Let's in the little bit of time that we have, I just wanted to tell you about another way of thinking about the equations of general relativity. Again, the complexity of actually carrying out the equations is too complicated, but nevertheless, the basic idea is there. One of the things I've told you and emphasized to you, particularly in classical mechanics, is that the principle of least action is the most central principle of classical physics that we have. All systems that we know about, mechanical systems, electromagnetic radiation, quantum field theory, all of these things, the standard model of particle physics, they're all governed by an action principle. And the action is something which in field theory, for ordinary particle mechanics, the action is an integral along the trajectory of the particle, so it's an integral over time. The action of a field is an integral over space and time. A field configuration is a value of the field at every point of space and time. So we draw, here's space-time, all of it. I've gotten it all down onto the blackboard. Time goes this way, space goes this way. Here's everything. A field configuration, or a field history, even better, a field history, is just labeled by, is basically a value of the field, or fields, at every point on here. So it's some field, let's call it generically phi, and it's a function of x and t, and that's a field configuration. Not every configuration is a solution of the equations of the theory, just like not every trajectory is a solution of the equations of motion. Every trajectory is a thinkable trajectory, but not every trajectory satisfies the equations of motion. In the same way, every phi of x and t is a thinkable possible value of a field in space and time, but they're not all solutions. And in general, to the best of our knowledge, every such field is governed by a principle of least action. The principle of least action involves some action, which is composed out of the fields. This is just a generic term for field. It's an integral. It's an integral over space and time, dx, dt. And x now means x, y, and z. So it's a four-dimensional integral of something, usually called the Lagrange density, which is a function of the fields and their derivatives. Let's call them phi sub mu, derivatives of the field with respect to x mu. And what do you do with this? You minimize it, or you make it stationary. You find the field configurations, let's use shorthand, which minimize the action subject to a constraint. You go out to in large space, some large distance, and some large times. You take some region of space-time, and you say what the values are on the boundary. It's the same deal as when you look at a particle motion, and you say, I'm interested in the solution, given that the particle goes through 2 points. Given that the particle starts someplace and ends someplace, then what's the trajectory in between? In the same way, you say, supposing you know that the field at some late time has some value, let's say final, phi initial, and you ask what is the solution which interpolates between these two. The answer will be the field that, or the solutions that make the action stationary. Okay, so the point here is that the field equations, the Einstein field equations, can be derived from an action principle. It's a long computation, but the action is simple. I'm just going to tell you what the action is, and then you can go home and try to take that action and apply the Euler-Lagrange equations to it and see if you can derive Einstein's field equations. I guarantee you it can be done. I also can tell you I never finished it. I started it several times and never quite got to the end of it. But it's just tedious. It's straightforward but tedious. All right, so you go back and you look at Euler-Lagrange equations. I'll tell you what the action is. It has some interesting pieces in it. First of all, let's do a simpler thing first. Let's just calculate the space-time volume. I will tell you what I mean. But, well, let's actually even think about ordinary space for a minute. Let's suppose we have ordinary space, and it has a metric, gmn. When I'm thinking about space, I use mn. Gmn dxm dxn. That's the metric, ds squared. The distance between two neighboring points is given by this formula. Now supposing I'm interested in the volume of a small region of space, let's say dx dy. Let me begin by supposing the metric has two components, gxx and gyy. And I have a small interval dx and a small interval dy. I want to know the area. We'll call it the volume. Volume means 3 dimensions. Area means 2 dimensions, but they're the same concept. Okay, what's the area of this little square? The area of the little square, I would know it if I knew the distance, the actual proper distance associated with dx and the actual proper distance associated with dy. All right, what's the proper distance associated with a little x dx here? Square root of gxx, square root of gxx dx. Can you read that? Let's make it bigger. This distance is square root of gxx dx, and this distance is square root of gyy dy. So what's the area of the rectangle? It's square root of gxx, square root of gyy. Dx dy. It's not just dx dy. The important thing is it's not just dx dy. No more so than the distance between 2 points is just dx or dy. The actual physical area is the square root, in this case, is the square root of gxx gyy. Now, I've used a case here where there was only gxx and gyy. There could be other components of the metric. If you work it out, this is a special case. This is a special case where there's no off-diagonal gxy term. Here, let's think of it this way. You have a metric, you have a matrix, gxx, gyy. Now, there may be some other components here, gxy and gxy. But what I tell you is that when there's no gxx and when there's no off-diagonal components, the volume element involves the product of gxx, gyy. Can you guess what the general formula is? What replaces that product? The determinant. The determinant is gxx, gyy minus gxy squared. The determinant is exactly right. So if you actually work out the volume element of a little square like this, or a little rectangle dx dy, the actual answer is not gxx gyy, it's gxx gyy minus gxy squared, which is the same as the determinant of the tensor G. It's usually just written with 2 bars to represent determinant and G. That's the formula for the volume element, or for the volume of a small differential dx and dy. What would be the, and this can be in curved space, this is in curved space or any space whatever, given a little rectangle dx dy in coordinate space, the area, or in higher dimensions it would be the volume, would just be the square root of g, square root of the determinant of g times dx dy. If I have some large region and I want the total volume of it, I integrate this. The integral of square root of the determinant of the metric times dx dy, that is equal to the area of the entire region enclosed within some boundary. What about the volume of space? If we're talking about volume, in other words, 3-dimensional space, well, it's exactly the same, except you have dz here. Exactly the same. Square root of the determinant of the metric is called the volume element. It's usually called the volume element. And if you have 4-dimensional space-time, it's useful to define a similar concept, which would just involve the 4th component. We call it the space-time volume. It's an interesting quantity. It's invariant. It's the same in every coordinate system. That's the important thing about it. If you re-coordinatize the region, change coordinates, this quantity stays the same. All right? The volume, in some sense, the physical volume of a region of space-time, or the physical 4-dimensional volume of a region of space-time. And this integral is an invariant quantity. Other invariants, other quantities which are invariant and which will not change when you change coordinates, are based on this quantity. If you take the volume element and you integrate it with any scalar, let's call the scalar s of x and t, dx dt, this also is an invariant quantity which doesn't depend on the coordinates. It's just the sum. You take each little volume element, you take its volume, and you multiply it by the square root, by the scalar field. You take the volume of each little element, multiply it by the scalar quantity in there, and add them all up. That's a quantity which is really not dependent in any way on the coordinates you use, even though writing it down may use a certain set of coordinates. All right. Action is a thing which is supposed to be invariant. Action in relativity theory is always supposed to be the same in every coordinate frame. Otherwise, the laws of physics which came out of it would depend on the coordinate system. If the laws of physics are supposed to be the same in every coordinate frame, one way of ensuring that is to make the action an invariant, a quantity which doesn't change from coordinate to coordinate, from coordinate system to coordinate system. So it's natural then to take the action to be, we'll call it d4x, meaning dx, dy, dz, dt, some kind, well, the square root of g the square root of the determinant of the metric, times some scalar. Now let's just take the Einstein theory without any energy momentum tensor on the right-hand side. Just pure gravitational field, nothing else. What kind of scalar could I put there? How many scalars are there that I can make up only out of the metric? Well, indeed. Right? So that's called R. It's the thing on the right, let's see, it's the, that's a scalar. Anything else you can think of? I'll tell you, there's one more thing. The other thing is any number, 7 or 4 or 16 or whatever number you like. So you can add to this a numerical number. Numerical numbers are always regarded as invariants. Everybody who sees 7 sees the same number. And the number that you put here depends on the laws of physics. It is a law of physics. It itself is a law of physics. Has a name. What's it called? All right, I'll tell you what its symbol is. Its symbol is lambda. Now what's it called? The cosmological constant. It's a term in the action which is just proportional to the space-time volume itself. The term in the action, lambda times this integral, is just the space-time action itself. The cosmological constant has not been, I have not included it in these equations here. These are the solutions, these are the equations without cosmological constant. So without cosmological constant, this is the action. And Einstein's equations are completely equivalent to saying minimize this, or make it stationary, make its variation equal to 0, away from a solution. That's minimizing something, is making it stationary. Yeah?
What's the stress energy tensor come into it?
The stress energy tensor would come in as additional terms in the action which would depend on the material and the other fields. For example, there could be electromagnetic energy, there could be other kinds of energy. They would come in as additional terms here.
So this is the vacuum?
Yeah, this is the vacuum theory. This is the vacuum theory, for example, the theory which would govern gravitational waves. Other things could be in here, but those other things would be made up out of different fields. They always have a square root of g, they always have a scalar. If you remember your electromagnetism, the electromagnetic field is described by an antisymmetric tensor, F mu nu. One of the things that you would put here would be F mu nu, F mu nu. That would govern the electromagnetic field. But let's leave that out. Let's leave that out. Here's the Einstein, the Hilbert-Einstein action, discovered, I think, just about simultaneously by Einstein and Hilbert. Of course, Einstein already had that. He already had the whole works and knew how it all worked. But they independently sat down and said, can these equations be derived from an action principle? And both of them, Hilbert and Einstein, both came up with the same answer. This is it. So this is a shorthand, but not just a shorthand, a physical principle that contains all the Einstein field. Incidentally, what replaces this field? I said a field in space. What do you put in there? The metric. The metric. This is an action that's made up out of the metric. And you vary the metric a little bit. You vary the metric a little bit, and you look for places where you found a minimum of the action. Varying the metric a little bit. If you vary away from a solution, the action should grow bigger in any direction that you vary it. So this is the Einstein-Hilbert form of general relativity. As I said, you could sit down. Let's see what you'd have to do. You'd have to calculate the curvature tensor in terms of derivatives of the metric. You do that by first calculating the Christoffel symbols, then differentiating the Christoffel symbols, multiplying them together, sticking them all together, multiply it by the square, do whatever contractions are necessary to produce the curvature scalar, multiply it by the square root of the determinant of the metric. It's a 4 by 4 metric, 4 rows, 4 columns. The determinant is a great big thing made up out of lots of components. Calculate the determinant, and then apply the Euler-Lagrange variational equations to that action. And it takes about 5 minutes, the whole operation, and out of it you will get Einstein's field equations. If you can't do it in 5 minutes, you fail the course. As I said, I've been trying to do it for 50 years, and I've never quite succeeded. No, a lot of my friends have, but...
There's a whole chapter in Tuve's general relativity notes, and it's very involved because it does all the things you talked about. And he plucks certain things out of the air because he knows the answer and then just verifies them. So it's really not easy.
No. As I've told you repeatedly, the principles themselves are not terribly hard. For whatever reason, somehow in the, there are people who have such a good visual feel for curvature and differential geometry that they can more or less see through it. You have your choice. Either you're a person with a great deal of visual ability to be able to see through the complexity of curvature tensors and so forth, and figure out how to do these processes by almost visualization, or you work them out by the algebra. So if you're good at algebra, you do it one way. If you're good at visualizing geometry and you have a great command of differential geometry, you probably can short circuit a lot of that. I frankly have neither. I am not very good at algebra, and I certainly don't have the visual ability to be able to visualize four-dimensional curvature tensors. So repeatedly I have sat down and tried to do this calculation, usually in the process of teaching the subject, and give up after about 2 hours. If I had to do it, I could. But since I don't have to, I don't. Don't ever tell any of my friends that I can't do it. Okay. Yeah, I know. They know I can't do it.
So this is not standardly written down in a text on relativity? Or
it probably is, but it fills pages. I'm sure it is written down somewheres. It doesn't help, because when you have a thing of that complexity, it really doesn't help to follow the steps from one step to another. Either you do them yourself and you figure out what the relation between the steps is, or you don't. A very long calculation really is not very illuminating unless you try to do it yourself, and then when you run into trouble, you peek. Oh, that's the next step, and then you understand why it's the next step. But I've never learned anything by looking at these long calculations. These days, people don't do them. People throw them on a computer, either numerically or analytically, and let the computer grind out because it's just too nasty and complicated. Yeah?
In hindsight, this seems more motivated than the way Einstein did it originally. But I'm wondering, I think it went from, 1905 to 1916 before he published General Relativity. What do you think, is it apparent from his papers, what was taking so long to put it all together?
The only papers I read were the early ones around 1907 and then the 1916 paper. And I read them, 50 years ago. So I really don't know what, but part of it is that very, very few people knew very much about Riemannian geometry. Einstein didn't know. He basically had to invent all of Riemannian geometry. I think one of his friends helped him with it who knew some mathematics. Was it Marcel Grossman? I don't know, but 10 years to put all of this together doesn't sound like a lot to me. He literally had to build all of the ideas of curvature, so it took a long time.
Aiming for that from pretty early on.
Yeah, I think he knew what he was doing pretty well. But you can go back and look yourself. The papers are in English. They were translated into English. You can find them. Okay. I think we're finished for the quarter. Yeah. Anyway, I could use a rest. I'm going to take a rest.
For more, please visit us at stanford.edu.